Okay, in this video we are going to be looking at gravitation. We're going to be looking big scale, so we're going to be looking at planetary gravitation and interaction between two large bodies. So if we start back looking at one of Newton's main thoughts, his thoughts were that every body in the universe is attracted to every other body. This tendency of bodies to move towards each other is what we refer to as gravitation. That is that tendency. So, since every single particle is attracted to every other particle, we could actually come up with a gravitational force with a magnitude that is going to be g m1 m2 over r squared. G is the universal gravitational constant, that's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. R is going to be the straight line distance between the two masses, and mass 1 and mass 2, those are the masses of those particles. Now, if we wanted to put a hat on this, what we're going to basically say is that this is along the radial distance. This is an attractive force. So this r right there, that is the radial vector. It really is often written as an r hat, as it's radially along the axis towards the other particle. It's not a magnitude bigger than 1, so this thing is basically 1 with a direction. So all that's doing is basically multiplying by 1, but giving the force its direction. Now, if particle 1 is attracted to particle 2 by a force F, and it is being pulled along this radial path towards particle 2, well, guess what? Particle 2 is experiencing a force of equal magnitude, opposite direction. So this is the force of 1 on 2, this is the force of 2 on 1. They are equal in magnitude, opposite in direction. They are pulling those particles towards each other. So that is what's creating a third law pair. So when we start looking at Newton's law of universal gravitation, this applies strictly to particles. So what happens if we're dealing with large objects? So if the sizes of the objects are small, relatively to the distance between them, we can still use this. So like the moon to the earth, the moon is much smaller than the distance between the moon and the earth. So we have that going for us. The other thing that we can look at is what's referred to as the shell theorem, which says that if we have a uniform spherical shell of matter, that is going to be attracting an object outside of the shell as if all of the mass was located right at the center. So although our Earth is not a particle, because it is a spherical in nature, it behaves as if all of the mass is located at the center of the Earth. Now, something that's kind of fun here to note, if we have an apple outside of the Earth and it has an attractive force, the Earth is actually just as attracted to that apple. However, because of the mass discrepancy, what you may notice is that the acceleration of the apple is 9.8 meters per second squared. However, the acceleration of the Earth towards that apple is on the order of 1 times 10 to the negative 25th meters per second squared. So that means the Earth is experiencing acceleration. However, it is so absolutely tiny, we're not going to be able to notice it. So here on 1, that is a ranking task, and I would like for you guys to look at that and to really consider that. And when we come back into class, we're going to be looking at what you come up with for this ranking task. So you're going to look at these objects and you're going to rank them in order from the magnitude of the gravitational force that they exert on a particle, greatest to least. So you just have a particle that's placed outside those masses. So one thing to consider when we are looking at a series of particles is that they are each interacting with each other. So here I have a series of particles. There are 5 of them. Mass 1 is 8 kilograms. All of the others are 2 kilograms. We know that A has a length of 2 centimeters and that our theta is 30 degrees. And we want to figure out the net gravitational force on particle 1 due to the other, that should be other type of particles. So what do we know? We are looking for the sum of all the forces. So that means we're looking for the force on 1 by 5, the force on 1 by 4, the force on 1 by 3, and the force on 1 by 2. So that is what we are looking at. And this is, of course, a vector quantity. So first things first, just the magnitude. Force on 1 by 3, that is going to be big G, mass of 3, mass of 1, over A squared. Force 1 on 5, so force on mass 1 by mass 5, that is going to be the same in effect. When we get to the force on 1 by 2, we're going to have G mass 2, mass 1, over, that is going to be a 2A, and that's going to be squared. The force on 1 by 4 is going to be G mass 4, mass 1, over 2A squared. Now, these forces, we're just going to look at mass 2 and mass 4. Forces here are pulling mass 1 this way and this way. Because mass 2 and mass 4 are the same, we're dealing with forces that are equal in magnitude, opposite in direction. So those are pretty much going to cancel out in our addition, because they are equal in magnitude, opposite in direction. Now, so 2 and 4 are going to cancel each other. Now we can look at 1 and 3. So 1 and 3 is going to be going this way. Let me change colors here for a minute. So we're going to put red out here. So that one's going to be going this way, and this one's going to be going this way. So if we look at our vector addition, we are going to end up with a resultant that's going to be going straight up. So the x components of those forces are going to cancel. So we're only concerned with the y components. So what we're going to get for 1, 3, we're going to get G. The first mass is 2, second mass is 8, over 2 centimeters, so that's 0.02. We're going to be squaring that. We are only concerned with the vertical piece here, which is going to be cosine of that 30 degrees. That is the only part we are concerned with. We are concerned with the y component of force 1 by 3. We are also concerned with the y component of force 1 on 5. They happen to be the same magnitude. So basically what we're going to end up with is that the sum of all of the forces is going to be 2 times big G times 2 times 8 over 0.02, that's 2 centimeters as a meter, cosine of 30 degrees, so it's square roots of 3 over 2. And that is going to be in the y direction, so that's going to be in a positive j hat direction. That's what's going to give us our vector. So that works out to have a magnitude of about 4.6 times 10 to the negative 6 newtons in the j hat direction.